Learn to earn for life.
Let us see the dynamics of synchronous machine. The transient stability refers to the maximum power flow possible through a point without losing stability with sudden and large changes in the power system. Following a sudden disturbance on a power system, the rotor speeds and rotor angular differences undergo fast changes whose magnitudes are dependent on the severity of the disturbance. For a large disturbance, changes in angular differences delta may be so large that the machines may fall out of step. Thus, the transient stability of a system predominantly depends upon the dynamics of the synchronous machine. Let us go through the dynamics of the synchronous machine. The kinetic energy of rotor is Ke is equals to half into I into omega square, where I is the moment of inertia in kg meter square, omega is the angular speed in radian per second, the angular momentum is m is equals to I into omega. Therefore kinetic energy is equals to half into m into omega in joules. Rather than having the moment of inertia of synchronous machine for dynamic studies, it is more convenient to use per unitized quantity called as inertia constant H. This is defined as the ratio of stored energy of a machine at synchronous speed to the rated apparent power of the machine, which is mentioned here. H is equals to stored energy in megajoules divided by machine rating in megavolt amperes. Let G is the rating of the machine in megavolt ampere, that is the MVA. Then G into H is equals to stored energy in megajoules. Hence GH is equals to KE, that is equals to half into I into omega square, that is equals to half into m into omega in joules, that is megajoules, where omega is equals to 2 pi f in electric radian per second, that is equals to 360 into f, that is in electric degree per second, or GH is equals to half into m into 360 f. Therefore we can write m is equals to G into H divided by 180 f, that is in megajoules second per electric degree, where m is also called as the inertia constant. Here the equation m is equals to G into H divided by 180 f relates the two inertia constants of the machine. For stability studies, it is necessary to determine m, which depends upon the size and speed of the machine, but H has a characteristic value of range of values for each class of machines. Typical values of H are mentioned here. For cylindrical rotor alternator, its value is 4 to 10. For salient pole alternator, its value is 2 to 3. For salient pole synchronous motors, its value is 0.5 to 2. Modern power systems have many interconnected generator stations, each with several generators and many loads. The machines located at any one point in a system usually act in unison. It is therefore a common practice in stability studies to consider all machines at one point as a single equivalent machine, having a rating equal to the sum of ratings of several machines considered to act together. The inertia constant m of the equivalent machines is the sum of the inertia constants of the individual machines. That is, m equivalent is equals to m1 plus m2 plus till mn, or h equivalent dot g base is equals to h1 g1 plus h2 g2 plus till hn gn. We can write it for h equivalent is equals to h1 g1 divided by g base plus h2 g2 divided by g base plus plus hn gn divided by g base. So this is the h equivalent equation. Thank you for watching this video.